This is my first video in a series in which we're going to start to explore the rate of change of graphs, which basically will lead into what we refer to as the derivative in calculus. But before we get there, we're going to go ahead and start with kind of a preemptive discussion about what we mean by rate of change. Okay, so when we talk about the rate of change of a graph, let's go ahead and get into this instantly here. Previously in our algebraic explorations, we talk about the rate of change of, say, a line as being kind of like its slope. So for instance, if we had some function of distance over time, we could say, well, how fast is this thing going, or how much distance is changing with respect to time? It was really easy to do. We could just find the rise over the run. Okay, so we say rise over run, this would be our slope, and that would represent our rate of change, essentially. We call this slope m. Okay. But we call that the rate of change. What we're going to start doing now is getting into rate of change of a graph that is not necessarily linear. So we could have a non-linear graph. So over here on the left, you can see that I've got a diagram here of a graph, for example. And what I want to do is compare the rate at which this graph is changing at all of these different points. Okay, starting with this first one down here. And what we can see is, as we read this from left to right, the graph definitely at this point has a positive slope, and it's kind of hard to see here, but what I've done is I've kind of drawn a line tangent to the graph at this point. The thing is, it's not easy to find the slope of a graph at one point. We could definitely find the slope of a graph given 2 points by counting rise over run, but we could say the slope of this graph at this point x1, y1 would be the same as the slope of a line tangent to the graph at that point. And we notice that it's a positive slope, so this graph must be increasing greatly. So if I'm going to compare the way it's increasing at x1, y1 to the way it's increasing at x2, y2, obviously it's still going uphill, we can see that it's starting to flatten out a little bit. So its rate of change is actually slowed down a little bit. Until we get to the top up here, this would be like, say, the vertex of a parabola. We'd say, well, what would be the rate of change instantly at point x3, y3? And we could say, well, that it's technically 0 because it's no longer having a positive slope. It's no longer having a negative slope. It's kind of leveled out. And then we get over to x4, y4, and this would be a point that has a negative rate of change. And the reason why is because over here our graph now has a negative slope. It's going downhill, okay? So the thing here is this. You notice that I used tangent lines to my graph to estimate or approximate the slope of the graph or how it's changing over time. So really quickly, I do want to review what we mean by a tangent line. Often I find that people are familiar with tangent lines through geometry, and we say, well, a tangent line is any line that goes through a point P that is on, say, the perimeter of a circle. You know, we say it's this line that glances across the circle at just this one point. But what I want to kind of infer here is this, that the slope of a graph at any given point, which, by the way, the slope of this graph changes from point to point to point to point. It's always changing, the slope of this graph. But it would have to be the same as the slope of the line tangent to the graph at that point. We call this the point of tangency. Okay. So if we want to estimate or approximate the slope of a graph at a given point, one way to do it is to sketch in a tangent line. Okay, we want to use a tangent line to the graph at that given point and say, well, what would the slope of this line be? Because guess what? We are very proficient at determining the slope of lines, okay? Not so much at determining the slope of a graph instantaneously at a given point. So for instance, I could say, well, let's look down here at this diagram I have here. I have 3 different situations, but we could say, well, what could we comment upon, or what are some things we could consider about the rate of change of the graphs at these given points? Well, one thing I know is at this given point P here, if I were to draw on this tangent line, you can see that I have provided a tangent line here. We say, well, this line is going uphill. So we could say that this graph is increasing. That's one thing we could say. Its values are increasing. We could also say it's got a positive slope. So its rate of change is positive, okay? And actually, the steeper the slope, the more it's increasing by, okay? So I look down here and I say, well, let's look at this. Obviously, at point P, we say that this graph has a negative rate of change because the tangent line is negative at this point. We could actually even try to estimate the slope of the graph at this point by estimating the slope of this line, but we have a negative rate of change. So it's a negative rate of change, and it is decreasing. Anything with a negative rate of change is decreasing its position over time. And last but not least, we say, well, noticing that the left side of this graph, if we were to put in tangent lines, very poor tangent lines I've just drawn, those are all negative. And the right side of this graph, we could say its tangent lines are all positive. We could say this, that this line right here at the vertex neither has positive nor negative slope. We could say that the graph has a constant rate of change for that moment in time. Okay, so we'd say 0 slope, 0 slope. I think I wanted to write 0, so 0 slope, and is a constant rate of change. It's neither increasing nor decreasing. So that being said, here's what we're going to do. We're going to use this idea of a tangent line to help us approximate, say, the rate of change or the slope of any given graph at certain points. So what I've got here is a situation where I say, okay, I want to use a tangent line to approximate the slope of the graph at this point. And this graph that we have in this case is just f of x equals x squared. So we can say also, y equals x squared. So this is some parabola. We could sketch it by hand. I intend to go over to GeoGebra and do this, but we say it's a parent function that starts at 0, 0. It's got an a value of 1, so it goes up 1, right 1. And also I know what its basic shape looks like, so it goes up 1, left 1. We have this right here. What I would like to do essentially is this: to the best of my ability at this point right here, 1, 1, I want to kind of approximate what the slope of this graph would be. Okay, so maybe we switch over to a different color here. We say, okay, well, what we could do is we could draw on a line tangent to my graph at this point. This would be my tangent line. I would say, okay, well, what is the slope of this line right here? Again, we're about to go do this in GeoGebra, but we can get a good idea here. It looks like I've kind of gone up 2 over 1 just by drawing this by hand. So I could say, well, is the slope of my graph right here, is the slope equal to 2? Maybe 2-ish. I don't know. So let's go ahead and draw this picture in very much graphically with a computer-aided device. We have f of x equals x squared. So here's our parabola. And I'm going to go ahead and drop in this point at 1, 1, right there. So 1, 1. The nice thing about GeoGebra is we can actually ask it to create a tangent line to this. We'll click on this point. So it goes through this point. We want a tangent to this graph. Here's our tangent line. And so in a normal instance, we'd say, okay, well, what is the slope of my graph at this point? Well, it'd have to be the same as the slope of the line tangent to my graph at that point of tangency. So if I had to find the slope of this line, maybe I can, for those watching on not very good viewing screens here, we could bold the axes, and I'll bold my grid so we can see this a little bit better. But we say the slope of this line right here, I notice that it starts at this point A. I want to go find where it runs into another perfect grid mark, and so I notice that it runs into, kind of looks like it crosses 2, 4. So we say, well, what would the slope of this line be? We could see that just by using segments here. From here to here I rose 2, and from here to here I ran 1. So the slope of my graph at 1, 1 would be approximately 2, and as a matter of fact, I'm just going to tell my audience here that it's exactly 2, and we could do this using the derivative. At this point, we just kind of want to establish that we could estimate the slope of graphs at different points. So here's what I have: about 5 million different functions to run through here, aka 6. And what I want to do is I want to use a tangent line method to approximate the slopes of these graphs at the indicated values. So not with a computer-aided device this time. This should be, by the way, f of x equals x cubed, not x squared. But I want to estimate the slope or approximate the slope of this graph at the point 1, 1. So here's what we do. We would go ahead and say, well, this is our point 1, 1. We want to approximate the slope here. So to the best of my ability, I'm going to draw in a tangent line. And this is me just kind of approximating and saying, look, can we come up with an approximate slope? And I notice that it almost goes to this point right here. So just like our squaring function, our cubing function here looks like it rises 2, runs 1. So at the point 1, 1, according to this tangent line, we could say the slope is approximately 2. And this is okay. I just wanted 2. I wanted to get an approximation, so 2-ish. Likewise, we say, well, what if we had a square root graph? The square root of x. What is the slope of this graph at 2, 4? So first thing first, we want to find the point of tangency. This is our point here, 2, 4. And the second thing we want to do is draw in a tangent line. So we could say, well, this tangent line, I'd say, look, maybe like this. Just kind of spitballing here. But we'd say, well, could I find another point on this tangent line? And again, knowing that my approximation is only that. It's an approximation. I'd say, well, maybe I think it goes through this point right here as well as this point right here. So in terms of its slope, we could say it's approximately 1/4 at this point. So my graph has a rate of change right here. Its instantaneous rate of change is somewhere around 1/4-ish. That's it. That's, maybe 1/3, or maybe, probably not 1/2, but we could say that it's somewhere in this ballpark. So this tangent line method works for all of these, even more exotic graphs, before you even get into the derivative. So I have some graph here, x squared minus 4x. We say the point 2, negative 4. So I'll go right 2, down 4. This one I put on here as kind of a gimme, but we say the tangent line. You'll notice that my graph is neither increasing nor decreasing right here. So its rate of change must be 0. That is, we could say given 2 points, it rose none and it ran 0. Okay, so rows none, ran 0. So we say the slope of this, or the rate of change at that point, is 0. It's not changing my graph at that point. This one's kind of a gimme also. I put this down here on purpose, but we say a line. At the point 3, -3, go ahead and find the slope of this graph. Now, if I were to ask you to make a point tangent to this graph, the wonderful thing is that the tangent line is actually the same as the original line. To have a line that confronts the graph only at this spot is kind of an impossible thing. So we'd say the slope of this graph is always 1/3. And that's the thing about linear stuff, is we say that the slope is constant. So it is constantly increasing at a rate of 1/3. Okay, so I got a couple more here. I want to look at these. In particular, the instructions here, we say, well, this is the graph of x cubed minus x. Approximate its slope at the point 1, j of 1, okay? So instead of writing actually, 1, 0, which is what I would get when I plug this in, I wrote 1 and then the y value that I get at that point. And we say in general, all points may be expressed thusly. We could say some point, some x value, and then its y value at that given x value. So we say at this point 1, j of 1, what is its slope? And again, we've drawn some tangent line here. We're just kind of approximating. It's not a very good line. I notice that maybe it goes through kind of right here, so it goes up 2, right 1. So we say the rate of change of this graph at this point is 2/1, so a 2-ish. And then last but not least, this is our natural log curve. We say let's go ahead and approximate its slope at 1, k of 1. So this is the most exotic one yet. And we say here at our x-intercept, if we were to draw on a tangent line, maybe looks something like this. And I notice that, hey, it kind of almost goes through this point right here. So the slope of this graph, or the rate of change at that given point, is approximately a rate of change, is a rate of change of about 1/1, or 1. Okay, it's increasing 1y for every 1x. But that's just kind of the basic premise behind finding the slope of a graph. We'll just use a tangent line instead. So in the next video, we'll go into a more formal definition of how we could use limits to make that tangent line really, really, really accurate. Cheers.